Yes, sir.
Okay. Hello, welcome all of
Hello.
you to the session 3. Um, in these sessions, there are some talks there. But it's basically 3 talks, and the first one is Rima Al-Ali. So she will be speaking on AC for CPS, and the title of the talk is a guide to support uncertainty awareness during during designing self-adaptive cyber physical systems. So let me quick introduce the Rima. So Rima is she's doing PhD or already completed. Mm, Rima, you already completed, I think.
Yes.
Yeah. So she completed her PhD from Charles University. Is a Department of Distributed and Dependable Systems, the Faculty of Mathematics and Physics, Charles University, Prague, Czech Republic. Her research focus is on the uncertainty in the cyber physical systems and the self-adaptive systems. She was involved in a couple of EU projects during her studies, which is related FP9, Marie Curie, ITN, and obviously the MPM for CPS, ICT cost actions, and mm, so you all know that there's a MPM for the CPS is one of the track for this for this webinar, and Rima was one of the very important key role on this project, specifically the Ensemble's CPS part. So now I'd like to start Rima, and the stage is for yours. So please.
Thank you very much for the invitation. I would like to present my interest in the research. Basically, I was working on designing cyber physical systems, where the cyber part is responsible for processing and the physical part is responsible for sensing and actuating. So such systems monitor the environment, they react to it, they influence the environment, which make it a bit handful for the developer to design. Let's take, for instance, a modern vehicle. As you can see that this vehicle is quite complex. It has a lot of sensors. It gets the observations about the environment. Depending on those observations, the vehicle decides to increase the speed or decrease the speed. However, each sensor has its own limitations. Ranges, imprecisions. For instance, if we take the radar is not able to detect the vehicle in front in case the road has hills or turns. Let's put such a vehicle in more complex scenario that would require collective behavior, such as platooning. The platoon usually are used in highways to increase the road capacity and decrease the fuel consumption. The structure of the platoon starts with the leader, who is responsible for setting the desired distance between the vehicles and the desired speed. This leader is followed by a set of followers which can join or leave the platoon dynamically. However, each vehicle is responsible for maintaining the distance between itself and the vehicle in front. It uses the sensors to accomplish that. The sensors are different from the operational modes that the vehicle uses. For instance, if the vehicle uses adaptive cruise control mode, it will use the lidar, radar, and the camera as sensors to measure the distance. However, in the cooperative adaptive cruise control, it would use additionally to those sensors also the data from the Wi-Fi. Does not mean that one mode is better than the other. It depends on the situation. So in case we have kind of problems in the communication in the Wi-Fi, then we will get unreliable data through the Wi-Fi, which make the safety of the system in question. In the case of adaptive cruise control, the distance between the vehicles is larger, so it makes the performance in question. So when exactly we can do such adaptation and how we can do that in the architectural level. So I focused as research questions on 3 questions. The first question is understanding what kind of uncertainties there already and how they are handled, which kind of methods that are used to handle those uncertainties. Then I needed to know how to identify those uncertainties to design the cyber-physical systems, then how to incorporate those methods to handle uncertainties in the runtime during the design time. So to answer those questions, I focused first on gathering the uncertainty informations from demonstrators, so I would be able to understand the situations much more. Then, depending on this knowledge, I would be able to have a guideline for the developers, how to design those systems, then how to incorporate at architectural level uncertainty awareness into the adaptation decisions, so it would be easier for the developer to actually design those systems. As the first step, I performed the systematic review that followed the guidelines in Kishenham, presented in Kishenham, from Kishenham. It starts in planning and then conducting and then presenting the results. However, usually the used approach is using peer-to-peer reviewed papers, and it was not sufficient for our case because such papers have only snapshots of the use cases. And what we would like to have is a full description of the demonstrators. To do that, we focused on projects, and the European Commission have a really nice structured frameworks for projects. So we targeted the ICT calls which have industrial leadership, which makes us able to see also the industrial view in those demonstrators. The review had to answer 3 questions. First, what kind of domains those demonstrators are in, the challenges they address, and what are the uncertainties there. So to perform this systematic review, we defined a set of keywords that follow in 3 categories. The first one is related to self-adaptation, second one is cooperative, behavioral, and third one, physical world interaction. The fourth one is just related to the demonstrators, so we made sure that at least we have 3 entities that communicating with each other to have a collective behavioral. So the selection started with applying those keywords on the titles of the calls and their description. Then we applied it on the project titles and their description. We made sure that, of course, the project is online and has deliverables, so it would be able to access the description of the demonstrators. And later on, we get inside the demonstrators and we check that the demonstrator have a collective behavioral and have interaction between the nodes, like not one to many, but like many to many, basically, interaction to have the adaptation decision. So as a result, we get 8% of the calls selected from the whole set in the ICT calls, then around 9% of the projects that are from those selected calls are selected as well. Then we go to the demonstrators, and around the quarter of the demonstrators were in the selection criteria. We end up basically with 12 projects there. The results are presented in two folds. The first one is related to the classifications of the data that we collected regarding the domains, the challenges, the uncertainties. This data formed the foundation for us to further reasoning about the relations between higher and lower aspects in the design. And depending on those observations, we also presented a taxonomy for the methods to handle uncertainties. So starting with the classifications, we saw that the domains of the demonstrators in the selected projects were have a variety, so we don't have like a really specific domain there, which makes the results more general. We have the challenges, which represented the border situations that could cause adaptation, where we grouped those border situations under properties, system properties. And then we went to the uncertainties, where the uncertainty source is more related to cyber-physical system part, and the uncertainty types and methods to handle the uncertainties are more related to the adaptation part. The results show that the most targeted domains are the energy and the traffic. The challenges are the resilience performance mostly, the source of the uncertainty mostly in changing resources, automatic learning, and the type of the uncertainty is violating operational boundaries, while the usually the methods that are used are more machine learning and statistics. So after we had this classification, we mapped the domains and the properties and study what type of uncertainties in this intersections and the methods are there. From that, we get a set of observations. Those observations tell us what kind of design properties or high level and low level concepts that or aspects that could help us in choosing the methods and what type of uncertainties are possible there. For instance, if we consider the computational level, when we have infrastructure as a cloud, so we will be able to use more storage and maybe train the method, while this is not possible in peer-to-peer communication. From these observations, we just propose a taxonomy for the methods to handle uncertainties. So additional to the uncertainty information that we need to know to decide what method to select, we need also to consider the input, output, and the assumptions of those methods. Plus, is it possible to use this method alone or with other methods to handle this specific uncertainty type? So from the systematic review, we get a set of data that we can learn from those projects, and the projects have different infrastructures. So basically it's more or less general. We get also observations from the mapping of the domains and the challenges and the uncertainty information. And then we propose a taxonomy for the methods that also coupled with set of questions to help the developer during selecting the methods to handle the uncertainties. Now the issue is how to identify those uncertainties during the design time. So for that, we need to understand more the self-adaptation phases. MapK Loop presented a really nice way to represent those phases, which starts with gathering the observations from the sensors, analyzing the data, evaluating the adaptation decision that when to or decide what kind of set of actions to do to reach the system goal, then executing this set of actions. All those phases depend on shared knowledge, which what we need to focus on, because this is the data that have the uncertainty. So to make it more systematic way and help the developer, we need to provide a framework for that. So we provide this framework that focus more on the knowledge, and we start with gathering the knowledge that comes from the sensors and goes to the effectors, plus the data that comes from the cooperation or from other components. And then we go to border situation, defining those border situations, the uncertainties in the data, what kind of thresholds that are taking part in the adaptation decisions, what kind of output that we would like to have from the methods that handle the uncertainties, and then we can form the adaptation decisions. So to help the developer to fill this framework, we also proposed a workflow that lead the developer step by step in filling this framework. So as an example, we can see the vehicle. The vehicle will have the data, for instance, Wi-Fi data from the sensor. Then we can say what kind of border situation that could cause the adaptation. And we identify the delays that exist in the Wi-Fi data. We have threshold, which is 5 meters, for instance, for the cooperative adaptive cruise control. And then we go to the estimation as expected for the method to handle uncertainty. So we estimate the Wi-Fi data. And then we define the adaptation decision. When we fill the framework, it will look like that. However, we still not able to see how the data flow goes with considering uncertainties. To do that, we propose also a lightweight notation, which start with data input, and then we go to identifying the uncertainty types, then selecting the methods to handle uncertainties to go to the adaptation decision as per. So we start with the sensors at bottom, and you can see the adaptation decision at top. And then we identify the uncertainties there. We then select the methods. Selecting the methods could be possible from the data set we gathered from the project, so we learn from them. And plus the taxonomy of the methods, which helps with set of questions that the developer should answer to help in the selection. So for instance, the Wi-Fi have delays, and then we need to select estimation method for estimating the data. Now the point is how to actually make the writing of the adaptation decision easier for the developer, which at the same time it will handle the uncertainty in it. So it will be uncertainty aware. To do that, we proposed operators, those operators presented by a set of APIs for specific kind of uncertainties, and we embedded them, or those operators are able to be used in the adaptation decision themselves. So to illustrate the idea, we return to the vehicle platooning. We said about maintaining the distance between the vehicles. However, there is another distance which is quite important. It's the braking distance of the vehicle, which is the worst case. So if something happened in front of the vehicle, what is the distance till it stops immediately? This is not the distance that we want to focus in Platon, because we have another vehicle in front, and to have better performance we need to have the distance as less as possible, which means the distance that we care about is if both vehicles stop, so the distance between them should be more than 0, which we call it as difference in braking distances. When we introduce this uncertainties in the scenario, we can see that the scenario changes completely. So for instance, if we have GPS signals for self-localization, instead of having one value for the position, we will have a range. Same goes when we have Wi-Fi delays, so it will be a range as well for the vehicle in front, the position of the vehicle in front, which means the difference in braking distances is also a range. So if we want to have the operators there, we can say that the minimum distance for this difference in braking distances is less than 0, then we need to have the mode switch. However, we still have a noise in data, so we need to also study the trend of this measurements instead of, or the calculations, instead of having just one value. To do that, we propose another operator that study the trend and gives the answer with a confidence level. Still, we have another problem, which is maybe this uncertainty would impact both modes that I'm in and what I'm switching to. So it won't make sense to switch in this case. To look into this situation, we need to learn from the output of the mode and see the correlation with the input. So we also presented another operator which studies the trend of the correlations in both modes and compare them to decide if a switch is needed or not. Then from here, we can take this operator and add it to the framework and update it. For the evaluation of the guideline, we wanted to show that the guideline is beneficial and could be reasonably applicable on different situations. For that, we decided to show two self-made examples and selected 3 representative demonstrators from the projects in the systematic review. So we will have different examples in each domain. The self-made examples, we made sure that we have the challenges coupled in such a way that the project did not represent. For instance, in that traffic, we did not have a demonstrator that have safety and performance at the same time. And when we selected also the demonstrators from the projects, we made sure that we had different kind of infrastructures, cloud, heterogeneous systems, or IoT there. And from the evaluation, we get to the conclusion that this guideline help us to have a systematic way for designing the components. And it does not matter if the infrastructure is different. And we can also use the data that is gathered from the project to help us in this selection of the methods. So in summary, I conducted a systematic review to gather the information about uncertainties in collective cyber-physical systems. From these observations in the results of the systematic review, I performed or presented a guideline for the developers to help them. Plus, we presented APIs to provide uncertainty awareness in adaptation decisions. Finally, we evaluated the guideline on 3 representative demonstrators from the systematic review. Thank you for listening. Any questions?
Thank you, Rima. And thank you for a nice talk. So I just check one questions from Slack. Let me check and you. So the one question is that can we not work with the uncertainties themselves instead of defining the operators? Or what if I estimate the uncertainty in real time and work according to the worst case scenario?
So I'm not quite sure I get the question, but I think the question was about handling the uncertainty at runtime, no?
The questions is from the uncertainty and the operator, and further in the real time basis the uncertainty estimator not. The worst case scenario that the participant is that asked.
So as I understood it, if the operators could be used for runtime and right or not, because I'm not reading the question.
I'll ask. It's my question. I'll ask you again.
Yeah.
So basically, what like when we are dealing with uncertainties, we are using operators so that you can make it like you can deal with that certain uncertainty and make it certain. So like if that particular situation is arising, then you go to some other mode like ACC, for example. And but what if I want to deal with the numbers themselves? Like, okay, I deal with certain thresholds. For example, suppose the minimum distance is, say, it cannot be, okay, the minimum breaking distance is less than 0. Then, why is there, like, basically my question is, can't we work with ranges, like, you know, a range of the minimum breaking distance instead of a fixed number?
This is what we used when I put the minimum. It's the minimum breaking distance because for us it's a range. So the operator returns the minimum value. And it's basically using the physical model of the vehicle. So I don't use the probabilities there. I know exactly where it should be because I'm calculating it depending on the physical characteristics of the vehicle.
Okay. Yeah.
Well, from the speaker room, is there any questions? Dominic, Professor Shorkar, Etienne.
It's all right. It's all right.
Okay. Thank you, Rima.
Thanks
you. For your talk. Yeah.
Thanks. Bye.
Yeah. Just going to the next talk. Speaker name is Etienne Borde. Is it correct pronunciation?
Not really, neither the first name nor the last name. Etienne Borde.
Etienne Borde. Okay.
No worries. I would probably fail trying to answer to pronounce most of your names, so don't worry. That's normal.
Okay, thank you. Okay. So, I just give a quick bio of Tien. That is, he is currently researcher at LTCI, the Telecom Paris State, and an associate professor at Telecom Paris. His activities focus on the software engineering for the real-time embedded systems. His research interests are component-based software engineering, architectural description language, model transformation, code generations, and formal verifications. So in his research, the Etienne applies and development uh, 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 such techniques to improve design methods of real-time embedded systems. The result of his work has been published in prestigious international conference. And the title of the talk of is the Architecture Analysis and Design Language, RAMSI, a MAD framework based on ADL for CPS design. So thanks, Etienne, for attending this and agree to deliver a talk. And nice to see you after a long time. Yeah.
Yeah, nice to
Somebody
see you
can-
too. Yeah. So, yeah, thank you for the introduction. I hope everybody hears me well and can see me as well. And if there is any issue, don't hesitate to interrupt me or if there are questions. Although the talk is only for half an hour, so I probably will have time only for 1 or 2 questions. The talk I'm going to give is about a framework that we're developing at Telecom Paris with Dominique and our team. And it's focusing on the cyber part of cyber physical systems. And the cyber part is becoming more and more complex, mainly because of technology evolution, hardware capabilities, and software complexity. The size of the design space is becoming huge. There are now security issues as well as well-known safety issues or requirements for these systems. And there exist actually many or numerous modeling techniques for the cyber part of CPSs. At the same time, we have shortened time to market. There is more and more competition in every field of cyber physical systems. And this leads to try to automate the design process. So it includes analysis, documentation, and code generation. But it also requires to reuse as much as possible existing functions. So we may talk about legacy software, but components in general. And I'm going to focus on ADL in this presentation. That's the language we use in our tools, in our research, as it is a suitable architecture description language for the cyber part of CPSs. It's basically dedicated to critical distributed real-time embedded systems. And the objective is to ease the documentation, improve designers' team communication. But we focus on the analysis of properties, the verification of requirements, model transformations, and source code generation. So basically, a model in software engineering is nothing more than a set of interconnected components. So the idea is to represent a design as an organization of components that represent software or hardware components. And we in our team mainly focus on the software part, as well as their interactions. So if you look at this picture rapidly, the only thing you see is boxes and arrows. That's pretty much the basis of model-driven engineering, but behind this there is a semantic and therefore many challenges when trying to automate the production of software from these drawings. So the boxes represent components. They are the main elements of the design. You have interfaces, mainly through ports here. I try to have this picture as agnostic in terms of language as possible. So we just see here that this component provides some output and this function requires some input. So these interfaces, they represent the contracts among components. This one has to receive some information to work, and this one can provide some information. And the connections will basically resolve these dependencies, these requirements, in a way that we can, in ADL at least, analyze some of the non-functional properties related to timing, safety, memory consumption, these kind of things. So all the modeling languages in software engineering follow these basic principles, and then you have different flavors depending on the field where you want to apply model-driven engineering. But in general, what we find in the literature is that the main use of these languages are specification, documentation, design, analysis, and code generation. Well, if I say these the main ones and I mention everything, then basically what I'm saying is that it can be used at every stages of the development process. But also, I think they are pretty much ordered in in how much they are considered useful in industry. I think one of the reasons is that the maturity of tools and methods are good or good enough up to this point, up to the design phase, and some may go through the analysis, verification, and code generation as well, but on some very dedicated domains or expressivity scope for the languages. So now I'm going to focus a bit on ADL. And as I mentioned before, the reason why we picked this language is that it's dedicated to the cyber part of cyber physical systems. And the reason of this claim, or the reason why we think so, is that it's dedicated to critical distributed real-time and embedded software-intensive systems. And you don't have so many languages that are dedicated to this field and that try to cover all the aspects of the design of such systems. So I'm going to give an overview of ADL by using an illustration on a Lego Mindstorm robot. That's one of the systems we can produce with our tools. That's also a system that we used in the summer school of the multi-paradigm modeling for cyber physical systems that was held in Pisa 2 years ago. And students had to model the software part of this line follower and generate the code from our tool, make some timing analysis to show it's correct with respect to the timing requirements, and then run the system on the field. What it does basically is that it follows a line from the light sensor that is here and has a distance sensor as well to make sure it doesn't go forward if there is an obstacle in front of it. So the general characteristics of ADL is that components, as for ADLs in general, I was presenting that earlier, are the main modeling entities. The components belong to one of the standardized categories. I will explain or list what are these categories a bit later. And categories are actually keywords of the language. So you will describe an architecture by using software or hardware components that belong to a category, and the keywords will basically say what is the category of this component. Then you can divide your the ADL definition or ADL model into component types, implementation, and composition, which I call here subcomponents. You can see types just like you would specify interfaces in an object-oriented language. Types basically describe how the component is viewed from the outside. What are the features, the interfaces for interacting with other components. The implementation is an implementation of a type, and it describes how the component is implemented either as source code, if it is a software component, or as a set of subcomponents, if you want to describe the inners of a component by going into the details of its internal structure. It's usually done using subcomponents. And what you do with subcomponents is actually represent instances just like you would have objects in an object-oriented programming language. So if you start from the root system implementation that you describe, system is one of the categories. If you start from the root system implementation and describe the subcomponents of an architecture, you basically describe the different objects. And so you find here something that is quite common in modern programming languages with the interfaces, implementation, and objects typically, or instances. Okay, and then inside the component definition, you will have different sections that are used to define features, properties, or subcomponents, which are also keywords of the language to define or to refine the different characteristics of your components. So let's have a rapid look at the different categories. You have two big sets of categories. One is the execution platform. The other one is the software component. So in the execution platform, you have basically or mainly processors, memory, bus, and devices. There are other components that I will not mention here. So processor is typically a hardware computation unit with task scheduling capability. So there is a part of operating system or runtime services embedded in the processor as it is when it is modeled. The memory is typically a storage component. You have buses for the physical communication links and devices for the interfaces or interactions with the physical environment. So it's quite descriptive in the sense that these components are typically the components you would think of if you look at cyber part, the cyber part of a cyber physical system. And it's also quite concrete in the sense that what you're describing is, or you're trying to describe by aggregating these components together is the actual implementation of your hardware platform. So if I take an example of this with the running example of the robot, what we do in the model of this robot is typically to consider that the brick here that actually embeds some display and some buses, but we model this abstractly as just one processor. We could go further into the details, but for the summer school, we don't really need more information than just saying that we have a computation unit here, and we have different sensors. So the color sensor to follow the line and sonar sensor to detect obstacles, as well as motors to run the wheels of the robot. And the buses will be used to represent the connection between the brick here, you see the port, and the different ports of the sensors. So that's for the hardware part. For the software part, we have different categories as well, like the data, subprogram, thread, and process. And again, they are almost self-explanatory in the sense that we describe concretely what we have usually in an application. And you see that you have both notions that are related to programming, like the data and the subprograms, but also notions of the configuration of an operating system, like the thread or the process. And typically a process is an application that is running on your system. So that's like just the definition that you have usually for a process. And it means you have a memory address space allocated for the execution of its thread subcomponents. Okay, so these categories, they focus mainly on the operating system and the programming elements of your software application. Again, taking the example we had before for the robot, we would define the data that is the light. Here it's just an abstract data in the sense that it's just representing an information. We say we have light that goes through the system somehow. We have a subprogram that is the function that computes the angle using a Ph.D controller. A thread that is executing the trajectory control, and the process, which is the application that follows the line. Obviously, what we need to do now is to say that the input of the angle computation is the light. It's executed by the thread, and the thread uses the address space. So what I'm trying to go for, where I'm trying to go now is that we need to compose these different components and connect these different components to actually represent the data flow of the application. So to do that, we have the notion of feature in ADL that is that helps to represent the interfaces of components. For subprograms, we have parameters, and for threads, we have ports. So we have the graphical representation here. I didn't mention that the graphical representation is a part of the language, and there is a graphical editor. I also forgot to mention that ADL is standardized, so all the different information that we see here is part of the standard and explained in the standard that is like 350 pages. And I'm trying to summarize this in about 15 minutes. Just giving an example, I'm not going through all the different notions that we have, of course. And so now we have defined the different interfaces, we can compose the components by saying that a process has subcomponents that are threads. So that's what we have here. So that's the first ADL code example that I'm showing. So it's a process implementation. So it means we have here a component implementation that is of the category process, and its type is proc that I didn't show here. You have different subcomponents. So here CTH is the control thread, and the control thread is in its implementation described as a call sequence. So you have different subprograms that are executed when the thread is active. Okay, and then by composition, you will show the data flow going through the different threads. So here you have the light sensor that is going to be called to provide light, and then the trajectory control will provide the angle to either another thread or to the engines. So to the engines, it must send a speed. So there must be a component in between here, obviously. Okay, and you have the different connections between the features that will explain how the data flow is actually implemented. So from there, we can do some analysis. Of course, I've not shown enough to do the actual analysis. There are plenty of information missing, but I don't have time to go into the details. But I'm just telling you that if we have enough information about the threads, we can do some timing analysis, making sure that they all meet their deadlines, which is their timing requirements. But we can also study the data flow to make sure that the time between the sensing of light and the application of the command to the engines is actually within a certain bound, either in terms of latency or in terms of jitter. So this is the type of analysis that we would do, given that we actually map the software architecture to the hardware architecture. So In addition to the data flow that I've shown here, we also have to express the fact that the line follower application is executed by the by the CPU, and that the sum of the data flow is going to go through the buses that connects the engine and the brick. So we have plenty of properties in ADL to show this, and we have even more properties. Most of them are standardized. And what I like to say about ADL is that even in the recent research that we have done about scheduling of directed acyclic graphs on multi-core architectures, we already found in the predefined properties, those that they are standardized, most of the information we needed to model the type of applications we were interested in. So except for minor changes or adaptation, most of the information we needed in our research on real-time embedded system scheduling was already present. I didn't mention modes and mode-specific architecture, so you have some reconfiguration capabilities in ADL. You have the notion of flows, which is used to analyze the worst-case latency and jitter. You have the possibility to represent distributed architecture. You have also state machines and error faults and propagation to do some safety analysis. So it's a very, very, very rich language. What we do with it, or what is our specialty in Telecom Paris, because so far what I've presented is the result of the standardization committee, and it's mainly led by the Software Engineering Institute in Carnegie Mellon University, Pittsburgh. But we in Telecom Paris, we focus on what we believe is a very important aspect of ADL is its compilation. So we focus on compiling ADL. So I put compiling in between quotes here because you will see that it's more than just a compiler. From the user perspective, you can see it as a compiler in the sense that Ramses is going to take an ADL model and produce the binary code of this ADL model. It's actually integrated in OSATE, that is the reference ADL IDE. But I was saying it's more than just a compiler because it's going through an ADL to ADL model transformation. So there is what we call ADL refinement in our tool, where refinement means that we add details into the model to have some analysis that includes the additional details that the compiling phase is going to produce. When I say compiling, well, it's then first the model transformation, then we have code generation, a set of code generation plugins that will target either ARINC 653 operating system. So ARINC 653 is a standard for avionics operating systems. And we have one implementation of it, which is called POC, that we developed at Telecom Paris. And we have the possibility to generate code and the configuration of POC. OSEC is also a standard that is used in automotive. And we have a port or the capability to generate code for NXT OSEC, which is one implementation of OSEC. And we also support POSIX and in particular Linux. Okay, we also have a set of analysis plugins, but if you want to, or if you think of the way Ramses is working, so it takes an initial ADL model, applies some model transformation, produce a refined ADL model, and the idea is that from this refined ADL model, the code generation will be very easy to maintain because most of the code generation is straightforward. It's made possible by the fact that we have this refinement phase before. So when we are here, we have a subset of ADL language that is very easy to translate to to code. And then it's also easier to port from one operating system to another one. But also we have a reduced semantic gap in the sense that by analyzing the refined ADL model here, we have more details in the model, and then we can include what the model transformation has done in the analysis phase. Well, if you take a step back, I mentioned it was a compiler, and I'm saying that the compiler is usually front-end, middle-end, and back-end. And I've presented something that is a bit more complex, and what is actually the compiler is just this part of the Ramses toolchain. And from there, from the source code, we basically reuse the compilers that are already existing. So what we provide is on the left side, it's the model transformation and the source code generation. And by using this abstract language that is ADL, we have more complexity because the design space is big, but also because we can have recursion. So the target model can become the source model of another model to model transformation. So the recursion is the potential problem here. We have complex objects in the model transformations. They are basically graph transformations, and Hana, just after me, is going to talk more about these kind of things. And because of the abstraction level, the kind of model transformations we can do is quite big. So here I have an example. If you open the box of the Ramses model transformations, you can apply some safety and security patterns. So we have implemented some safety patterns. You can deal with remote connections to then use the output model as an input model for dealing with operational modes. And then you can deal with the local connections between the threads. So local means threads that are in the same process. And for each of these steps, you can have different variants here that represent more or less the design space. And each of the model is amenable to a type of analysis. And depending on the level of abstraction you're in, some analysis will provide some reliable results and will be applicable. And in some other abstraction levels, maybe the analysis is not even applicable and or would just give some non-reliable result. So just in a nutshell, it's a compiler, and you have to define the ADL model, but it's going through model transformation, analysis, and code generation, as I was just explaining. It's a compiler in the sense that from the ADL model, you will eventually produce the binary code, and that was the assignment of the summer school with our example of the robot. That's typically the kind of architecture that you would have graphically, and you can use Ramses almost like a press button tool to then produce the software application. Some of it will still be, some of the software will still be implemented manually. So that was my presentation for today. I went very fast on the notions, so there might be things that remain fuzzy. If so, then please ask questions, and I will try to clarify what I was saying.
Yeah, thank you, Etienne.
You're welcome.
So in Slack, just check Slack. Unfortunately, in Slack, there is no question.
I don't know if it's unfortunate, but we have no question.
Yeah, but I have some questions, and obviously, yeah. I hope Professor Sholkar has some questions.
Okay.
Professor Sholkar?
Okay. Actually, in your slide, could you come to the very first slide?
Yes.
No, not this one. Next one, there is some function flow. Yeah. So essentially, you have talked about this function 2 and function 3 vis-a-vis function 1. there is a bifurcation. Does it mean parallel invocation of these two functions?
Well, that's a good question. Then, so it really depends on what type of dependency you express with the connection here. And in ADL, you have you can express three types of dependencies. The only one that makes the connection a precedence constraint is when you have here what is called in ADL an immediate connection. And then when you have an immediate connection, it means that both function 1 and function 2 have to wait until function 1 has given a new fresh information to work with. So if those two are immediate, then only these two can be parallelized, but they must wait. So that's you have a graph with precedency constraints.
Okay, some kind of data flow dependence.
Yeah, exactly. But this one, if it's not immediate, then it's not a precedence constraint, and you could run function 1 and function 2 in parallel without having one to wait for the other.
Yeah, but this arrow from function 2, function 3, does it mean that there could be intermediary synchronization requirements?
Yes, exactly. So, I mean, when I say yes, I mean there might be some race condition, and then you have to use some things like logs, for instance.
Okay.
And all these discussion here would have an impact on the type of results or the precision of the results you would have from a data flow analysis or from a schedulability or timing analysis. So these are the kind of details that we'll look at more precisely when we refine the ADL model.
Okay. Now, coming to slide 18, I suppose. Could we just...
Yes?
No. After this, is it? Yes, the refinement.
Mm-hmm.
Now, here, so essentially your refinement is because of ease of code generation, as well as ease of analysis. I mean, there are two objectives possibly.
Yeah, absolutely.
Yeah. Okay. Now, these refinements are correct by construction, or or you have some kind of scope for proving that yes, these refinements are correct or something like that. They are automated.
No, yeah, they are automated, but unfortunately, they are not. I cannot claim they are correct by construction. The reason is that we mainly focus on the timing analysis, and at the refined ADL model, what we include is actually the implementation or a model of the implementation of the runtime services. So everything that is related to the functions, the system calls. And that's why we do the analysis at the refined ADL model. If it was correct by construction refinement, we could have done the analysis here in the initial ADL model, and we wouldn't have had to do it again here because we would have proven that the previously analyzed requirements are preserved in the refined ADL model. But that's not the case, mainly because here we don't have all the information of what is going to happen in terms of additional information in the ADL model. We could have some. I mean, that's a very interesting topic, but to answer more briefly to your question, yeah, no, it's not a correct by construction refinement here.
Okay, so there could be that in the initial model we annotate some specification, and then yes, in the refined model through more detailed analysis, you could have scope for proving those properties. That kind of things could be
Yes.
Possibly some kind of user-specified properties pertaining to timing and things like
Yes.
that. Yeah.
Yes.
Okay, there is another thing that I wanted to say that basically, you have this. This is obviously there is a programmability aspect because you have this language which user can manipulate. For example, in your robo, what I am interested in knowing that the robo that you have used for your summer school, etc.
Yeah.
What kind of application spectrum that you have covered? Like line follower is what you have said. Then some kind of close contour following, something like that. Do you have scope for all these covering spectrum through programmability?
I'm not sure I get the question well,
I'm
because
telling, yeah, depending upon some other application which are on the same, I would say similar application, like say a close contour.
yeah.
So that the user gives the contour,
Okay.
and and gives the contour in the sense that there must be a program involved in specifying the contour,
Yeah.
and the robo will be able to follow that contour.
Yes.
It should be there, right?
Yes. 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 Yeah.
That is there. Fine.
Yeah. Yeah.
Okay. And another thing is your, basically, you have been using certain processors.
Yes.
And suppose you change the processor.
Yes.
That means in the lower level component, like your hardware components, suppose you go for another processor. So this being a language, is there any scope of adapting to other processors, at least within certain spectrum?
Yes, so there is a way in ADL to specify that the timing properties that you give is correct in case you have deployed your software into this specific processor. So you could enhance this by adding new processors to your model and saying that these are the timing properties that would be correct for this new processor. And then for the building phase, we mainly rely on the compiler. So you need to have, of course, the compiler for the generated source code for the new processor, as well as, of course, the port of the operating system for the processor. But from a modeling perspective, yes, you can say that the information you give is correct, assuming you have deployed on this or that processor, and you can enhance this quite easily.
Okay. That's all I wanted.
Okay. Thank you. Thank you very much.
Etienne, I have just one question. It's a very short question. So this analysis is basically the timing analysis only. That is the for example, the host case execution time. So this type of the analysis you are doing on the refined ADL model.
Yes, that's what we focus in. Yes.
Okay.
Yeah. So typically what would be interesting in terms of refinement, and that's why I said that it's not correct by construction with respect to timing analysis, but there are probably techniques we could use and enhance to make sure that the model transformation is correct with respect to other types of properties.
Oh, one thing the people said doing, actually we are trying to do, that is from the initial ADL model, if we construct the type graph, and the refined ADL model, if we construct the type graph, then using some graph transformations property checking tools, for example, the groves. Is it possible to check some property, for example, the safety properties? So because in some initial model, if some anti-patterns is there, so if we analyze these anti-patterns, the anti-patterns with the safety, security, scalability, the reliability, this sort of things. So whether it is possible or not, I'm just asking you. So.
Well, I'm not sure I can. No, I cannot answer this question that easily. I'm not sure.
Okay.
I mean, that's
okay. We will discuss it offline. So
yeah, with pleasure. Yeah.
Thanks for your time.
Thank you.
Yeah. So our next talk is again from the Telecom Paris. Dr. Hana. She obtained an engineering degree in computer science in 2013 and the PhD degree in the computer systems engineering in 2019 from the National School of Engineers of Safed in Tunisia. She is currently doing a postdoc at Telecom Paris, France since 2018. Her research interest focused on software engineering, model transformation, real-time systems, architecture, description, language, and the formal verification. So I just, the title of the Hana's talk is the Incremental Model Transformation Tools for Models of Rich Language. So Hana.
Hi, can you hear me?
Yeah, we can hear you. So
do you see my screen?
Yeah, we can see your screen.
Good. Okay. Thank you for the introduction. Thank you for inviting me for this meeting. Today I will present my work in the context of model transformations, which are one of the fundamental topics in model-driven engineering. Precisely, I will present the result of our benchmark about a set of incremental model transformation using models of rich languages. So we all know a traditional model transformation that ensure always the batch transformation where the target model is regenerated from scratch after any change in the source model. Now, the incremental model transformation allows to only update the part of a model that need to be changed. So if I have one element in the source model is changed, so only one element will be updated in the target model. So this is obviously improve the performances in terms of execution time of the transformation. However, the question is how those incremental tools are suitable for modeling large and complex systems which reach modeling languages as required by the industry. So, in fact, there is a lot of incremental model transformation with different transformation specification language, different execution engines. So they differ in their specification capabilities and their runtime performances. Also, there is a lot of classification and benchmarks that have been published, but the problem is that they only use simple examples. For example, as you can see here, the family to person benchmark, it has only few classes, so there is no evaluation with complex model transformation for large industrial system modeled with range languages with complex structure. So our objective is to study a set of incremental model transformation using realistic models written with languages that are really used by industry. So the idea is to define a benchmark with rich language with complex structure and using complex transformation specification. For this end, we choose the AADL language, which is a component-based language for embedded real-time systems. It is a standard language used in many domains, such as avionics and e-health. So as you can see in this slide, we have a sample example. AADL allows to modelize the system as a hierarchy of hardware and software components with their interfaces and their connections. Also, we choose to use the EUSAT tool, which is a reference implementation for AADL modeling and analyze. So EUSAT provides two meta models to deal with AADL language, which include more than 270 meta classes, which reflects the complexity of AADL language. So in the context of architecture description language, there is a strong need to model transformation for different purposes. For example, model analysis, for code generation, for model refinement, etc. So in our benchmark, we choose a model refinement based on the Ramses tool presented by Etienne Borde. So Ramses is a code generator for ADL system. It is implemented using the ATL language. Actually, it's a big model transformation with more than 1,000 ATL rules. So in our work, we only consider the Ramses communication refinement, which defines how ADL port connections are mapped into shared data. So a challenge in this rule is that we should consider several options for ADL connection. For example, there is 3 kinds of connection. For port connection, we have different port feature types, different directions, different type of connection ends, and we may have connection declared at system level and other connection declared at process level. So, as you can see, using or working on chess model transformation like Ramses and the ADL language are suitable, and we can study incremental model transformation in a context representative of industrial application. Okay, so now I will present the our benchmark through its 4 phases, starting with the selection tool. So those are our criteria. Since we use OSAT, so we restricted our selection to tools that are based on the Eclipse modeling framework, de facto standard. Also, we eliminated not mature or not maintained tools, so to eliminate problems due to bugs and to be able also to obtain support from tool providers. So in the context of incremental model transformation, we find some extension or some incremental extension for the ATL language, like reactive ATL and ATOR. However, despite the maturity of ATL language, those prototypes are not mature to support the Ramses communication refinement. So we eliminate those tools rapidly from our benchmark. Then we find also a well-known tool, Vietra, which is based on the event-driven programming paradigms. Also, we find a set of tools that are based on the triple graph grammars, mode, imflon, TGG interpreter, imorph. However, we quickly eliminate TGG interpreter and imorph because they are no longer maintained. So, as a result to this selection phase, we decided to work with 3 models, 3 tools. So we have Mode, which is a tool for incremental bidirectional model transformation. Mode makes use of graphical concrete syntax for TGG rules, and we can also add OCL expression to assign attribute and to add constraints. We consider also the imflon tool, which is an open source for incremental bidirectional model transformation. So imflon provides a textual syntax for TGG rules, and we can add some set of predefined attribute condition to assign attributes. Finally, we have Vietra, which is an open source tool for incremental event-driven model transformation. So Vietra makes use of the extend language, which is a dialect of Java, and provides also a new language, VQL, to express queries or patterns which are considered as pre-condition for rules. Okay, now I will present the benchmark specification based on the Ramses communication refinement. I will start with the port connection rules. As you can see, we have 2 cases. If the port connection is declared at process level, we will add a data subcomponent in the process shared between the source and the destination threads. Also, if we have a port connection declared at system level, we will add 2 data subcomponent for each source and destination thread in each process. So we note that Ramses does not consider the devices, so the port connection declared between threads and devices are preserved. Also, the rest of the model, of course, should be preserved. So we define a set of copying rule to just copy each element, each component from the system, ADL system, to the target ADL system. Okay, so at this stage, we have defined the benchmark specification and selected the benchmark tool. Now I will present the different solutions, starting with the mode tool. So as you can see, mode specify model transformation using a set of TGG diagrams. So in this slide, this is the TGG diagram for the port connection rule, or port connection that is declared at system level. So here we have three parts for the source model, target model, and a third traceability part, which contains a set of nodes of correspondence between the source and the target models. So we have boxes which represent the element of source and target model and the nodes of the correspondence domain. So black, we have colors. Black boxes are for the context, object, and nodes that must have been created by other rules. And we have green boxes that will be applied, will be created by this rule. Also, we can add OCL expression. For example, here we check if the kind connection is per connection. Okay, so this is the same rule, but specified with the imoflang tool. So as you can see, we have the three parts for source, target, and correspondence models, but in the textual syntax. Also, we should add a fourth part, which is attribute condition. So here we can use the predefined set of attribute condition, as for example, the equality between string. Finally, this is the solution using the Viatra tool. So the specification is composed of a set of queries or patterns. Here, for example, we have the pattern for the port connection rule. So this pattern allows to find the required match of element to apply the rule. Then this is the rule. It is specified using the extend language. We have three main parts for three actions: created, updated, deleted, to add a port connection or to update a port connection or to delete a port connection from the target model. Okay, this is just some observations about the model transformation languages of each tool. So, for example, for TGG tools, we should note that learning effort for TGG is required, especially for users who are not familiar with graph transformation. We note also that those two tools provide examples, documentation, and handbooks to introduce this approach. We note also that a serious problem with mode is the complexity of graphical TGG diagrams, especially when we deal with complex rules like the port connection rules. It becomes hard to understand and maintain with many nodes and many links. This is not the problem with imoflang, since we have a textual syntax for TGG rules. Also, we note that imoflang is the only benchmark tool that provides mechanism like the rule inheritance to factorize model, common rule parts into abstract super rules. Okay, regarding the Viatra tool, so extend is a rich language like Java, and it's easy to learn and to understand for Java programmers. However, we should note that all the detailed actions should be specified using the Viatra API for transformation to add, update, or delete each element in the model. Okay, now we reach the runtime performance evaluation. These are our criteria. Donc, unlike existing benchmarks who only focus on the scalability according to the size of source models. We also consider two other criteria. We consider the structural complexity and how an ideal complex model structure, like hierarchies and topologies, may impact the runtime performance. Also, we consider the transformation specification complexity, means if the runtime performances are impacted when adding more complex transformation rules in the specification. Okay, so to consider all those criteria, we define a test suite that includes more than 200 test cases. So we define a set of AADL models to represent different AADL structure, different power connection declaration level, different topologies, different hierarchy levels. Also, we define a set of AADL model that scale from 2 to more than 500 per connections. Also, we consider an industrial case study, which is the largest AADL model in this benchmark. To consider the transformation specification complexity criterion, we defined two specifications. The first one for copying specification that just consider the copying rule to copy the target, the source into the target model. Also, we consider the refinement specification that adds the per connection, the Ramses per connection rules to the copying specification. So, finally, for the execution, we define 4 scenarios. The first one is for the batch transformation. So here we add an ATL test so we can compare our benchmark tool with the non-incremental tool. Also, we have 3 incremental transformation scenarios. So addition, update, deletion, when we add a per connection, and when we update when we change the name of the per connection, and finally when we delete the per connection. Okay, now I will present the results of the runtime performance evaluation, starting with the structural complexity criteria. So as you can see, this table includes the runtime, the transformation runtimes for mode, Imuflon, Vietra with structural tests about the batch, addition, update, and deletion scenarios. So we have colors. The highest, the fastest runtime is in green, and the slowest one is in red. So when dealing with small models, Mode, Imuflon, and Vietra have short execution time. Only a few milliseconds are required for each scenarios. But in general, we note that Vietra is the fastest tool and Imuflon is the slowest one. Also, we note that increasing the number of hierarchy levels does not impact the run times of the different scenarios. Now, these are the results of the model scalability criteria. So here we have the runtime transformations of the scalability ADL models. This is the batch transformation scenario for Vietra, Mode, Imuflon, and ATL. So ATL is the fastest tool when dealing with small models. For large models, the performance degrades rapidly, and ATL cannot handle models with more than 64 per connection. Now, about the incremental tools, Vietra is the fastest one when we deal with small models, while Mode scale better with large models. We note that Vietra and Imuflon have problems, memory problems. They cannot handle models more than 8 per connection and 128 per connection due to an out of memory error, which explain also the results about our case study. So as you can see here, Imoflow and Vietra failed the test for the braking system, and mode is the only tool that can transform the braking system model in less than 5 seconds. Now these are the results of incremental transformation for addition, update, and deletion scenarios. So in general, Vietra is almost the fastest tool. We note that Vietra and mode transformation runtimes are nearly independent from the model size, which is not the case for Imoflow, that rapidly shows memory problems from the model with just 8 per connection. Now, finally, the results of the transformation specification complexity criterion. So here the table includes the results for batch addition, update, and deletion scenario according to the copying and refinement specification. So we note that the execution runtime are increased from the copying to the refinement specification in all the benchmark scenarios. Also, like the sectoral test, Vietra is the fastest tool and Imoflow is the slowest one. So here just I put the summary of the runtime performance evaluations. Our result shows that the runtime performance of the benchmark tool depend on size of models and the complexity of the transformation specification, but not on the number of hierarchy level or the connection topologies in the ADL model. We note also that mode offers good runtime performances. It is the only tool that succeeds in all the benchmark tests and more importantly in the transformation of the industrial case study. We note Vietra runtime performance decreased with large models due to memory consumption problems. Imoflow also have serious runtime performance problem even for small models. So this was a presentation about our benchmark for a set of incremental model transformation based on the Ramses model transformation for the ADL language. So this benchmark is available online for user and for user and tool providers. So we note that all the benchmark tools are able to specify complex model transformation. Mode and Vietra scale well for complex model transformation and relatively large system, especially in the case of mode. However, we note that 2 out of 3 benchmark tools are unable to transform the industrial case study, which shows that these approaches are not yet ready to be used in industry. Okay, as future work, we aim to extend our comparison in by considering more important criteria such as the loss, the information loss, and the memory consumption. Thank you.
Thank you, Hana, for a nice talk. So I just check Slack of whether there's any message on there. Yeah. No, there is no questions from the audience, but I think from the speaker room, we expect some questions. Professor Shorkar, do you have any question?
Yeah, just one question that all these tools are available online, is it? Your ADL language as well as model, all these are available online?
Yeah.
Okay. Okay. Okay, that's all. That is all I wanted to ask.
Okay, and Hana, I have just one question. So, will you? So, your motivations is to make some tool chain to make these the to make a basically the combinations of the model transformation tools, I think. So is it the compositions of the tools are you doing?
Sorry, what was the question?
So main motivations of your work is to make a tool chain. Am I, if I understand correctly? So is it your main objective? I think.
No, the main objective is to study those tools and test them in real context representative of the industrial, and we want to test them if they're really suitable for modeling with large and complex languages.
So incremental model transformation tools. So it takes the source models as well as. So what are the input? Can you please repeat once again? There is what is the input for the IMT? It's only the source model, or
Yeah, there is a source model and there is a transformation engine. He will generate the target model. So here, if it is incremental, he will just change the element in the target model without regenerating all the target model from scratch.
and my another question is what kind of model transformations rules are you looking for?
Well, we can use any type of models or languages, but here we use the language because it's a rich language and it allows to really test those tools.
Okay, so you're using the OSATE also. Okay, and okay, fine. Okay.
But maybe I can add something, Soumyadip. The idea here is that these transformations are the ones based on the ones that are applied in Ramses. And right now, Ramses is using for model transformation tools a tool called ATL. And as you can see from the benchmark, this tool doesn't scale at all for large models. So the idea in the long run is to replace these transformation with the best tool that we can find. And that's why we did this benchmark. And the other idea also is that if we select one of the TGG tool, which is graph-based, then maybe it may help us to do some verification on these transformation, thanks to graph transformation theory.
So then we can apply that is the inductive based approach or the K-induction for this graph.
Yeah, similar approach like those that Holger works on in his group, basically.
Okay, thank you, Hana.
Thank you.
Thanks for your time. So this is the end of this session. We'll meet the 6 o'clock. That is the next session. It's a session 4, and it consists of the 2 talks only. One from the MPM for CPS track, which will given by the Didier Bouches, modeling and verifying of the CPS, and another is AC for CPS track. Dr. Shantanush will give the talks. The title of the talk is Cyber Physical Systems Driven Digital Twins for the Industry 4.0. Okay. Thanks for attending. Thank you.